You saw the title, you know what time it is, the people asked for it, and I'm delivering. So today we're just going to do some topology proofs, probably like 3 of them. The first 2 will be pretty straightforward. The third one, not so much. It'll be a little more extensive and require a lot more explaining on my part, especially if you haven't studied in topology or haven't really been introduced to it. It probably would have made a little more sense for me to do an intro to topology video first. But the people asked for proofs, so I'm giving them. So at some point I would like to do an intro to topology and an intro to graph theory videos like I did for group theory and linear algebra. But for the moment I'm going to do this. So let's hop to it. Alright, so the first thing we're going to be doing is verifying that a set of elements forms a basis for a topology. So in order for something to serve as a basis for a topology, it needs to cover the entire space, number 1, and number 2, the intersection of those basis elements have to be such that they can fit another basis element arbitrarily in them. So in this example, we're talking about the set of intervals from A to B with an R, so just on the number line, such that A is less than B. We want to know if it actually forms a basis on the number line consisting of real numbers. So the first thing we have to do is check whether or not it covers the entire space, so all of R in this case. So we have for every x on the number line, we can make an interval, an open interval around it. There exists some interval x minus 1 to x plus 1 such that x is within this interval. It's important to note that this is an open interval, so because it's an open interval and it doesn't include these endpoints, we can make it arbitrarily small and we can make it fit the entire space. So that's our first one. So no matter what x we have, we can make an arbitrarily small. In calculus and analysis, we'll use epsilons, but we don't really have a concept of distance in topology for the most part, except for perhaps when we're talking about metrics and metric spaces. But we can make this arbitrarily large or small so that it fits in any size space that we need to. So we make a very large interval around a point or a number, we can make a very, very small one. So the fact that we can make it any size means it qualifies. And then part 2, we need to verify that the intersection of intervals like these can also fit intervals within them. This seems pretty intuitive, maybe a little trivial, but still got to show it to be sure. So we're going to say for every 2 set of intervals from A to B and an interval from C to D within this set of basis elements B, there's going to be some x which resides in their intersection. So from A to B, intersect C to D. Since they intersect, that means there exists some interval from C to B, which is also in this set of basis elements, because we said this is consisting of any open interval, such that an arbitrary x is going to be within this interval, and this interval is going to be a subset of this intersection of these 2 original intervals. A little bit redundant for me to write this, but do it just for the sake of it. So now we have that no matter what our x is, in this case real numbers on the real number line, we can draw an arbitrarily large or small interval, which we call neighborhoods in topology, around it, such that an x will always fit in it, and we will have one for every x arbitrarily. And secondly, we showed that if we have the intersection of 2 intervals, which we're calling our basis elements, we can find an x, find a number, which resides in their intersection, and that intersection will be the open interval from C to B. Since we have the intersection of open intervals, their intersection will be open as well, which will be another basis element, such that our random number will be in that element, or in that interval, and that interval will reside, like we said, in the intersection of these 2 original intervals. So we're good. All right, for the second proof out of 3, we're going to show that if two spaces are homeomorphic, then if one of them is homeomorphic, then the other one must be homeomorphic, because homeomorphisms are similar to homomorphisms in group theory, and they preserve what we call group structures or structures in spaces, and that includes being Hausdorff, being isometric, having cut points, limit points, and all those other kinds of stuff we're not going to talk about today. So let me draw a picture real fast. All right, so we have our two spaces x and y. We're going to show that if a homeomorphism exists, then if x is Hausdorff, then y must also be Hausdorff, and vice versa. So we have 2 points over here. We have y1 and y2 in our space y. We have two functions. F takes us from a point in x to a point in y, and f inverse takes us from a point in y to a point in x. And we have y1 and y2 in y, and over in x we have their preimages, which I'm calling f inverse of y1 and f inverse of y2, and those are the neighborhoods of the preimages of those points. All right? So we're going to establish a few things first, the first of which is we want to establish that y1 and y2 are disjoint points. We also want to establish, since it's in our given, that f is homeomorphic, so I'm just going to write it here just for the sake of formality, and we have f from x to y being homeomorphic. And we also have that x is Hausdorff. So if a space is Hausdorff, that means there exists 2 points such that neighborhoods, open neighborhoods, can be drawn around them, and those open neighborhoods are disjoint, which is to say they do not intersect, or they do not intersect non-trivially. So they can intersect, but only if it's the open set. So it's simpler just to say they don't intersect, because usually if something intersects trivially or happens trivially, it's not interesting, it's not of much benefit to us, so we just don't even bother with it. All right, so we're going to refer back to the picture now. So since x is Hausdorff, like we just said, for any 2 points, there exists some neighborhood around them such that those neighborhoods don't intersect non-trivially. So we're going to call these 2 neighborhoods, which are the preimages of these 2 points, y1 and y2. So we have f inverse of y1, its neighborhood, and f inverse of y2, which is the neighborhood of y2 in x. So that means some 2 neighborhoods exist around the preimages of these 2 points in x such that they do not intersect. So, all right, I have that written here. I did some abbreviating. I'm additionally going to name these 2 neighborhoods here. So f inverse of y1 is going to be u1, and the neighborhood around the preimage of y2, this here is, I'm just going to name it u2. We usually abbreviate neighborhoods as u and v, uppercase. So now let's talk about what these neighborhoods can do for us. If we apply f to these neighborhoods, it's going to take us to neighborhoods around these 2 points respectively in y, which means they're the inverse of their own inverses. So f of u1, if we apply f to u1, it's going to take us to some neighborhood around y1 and y, and that's going to be the same thing as taking the inverse of this function, which takes us from y to x. So the inverse of a function which takes us from y to x is going to take us from x to y. It's going to be the same thing, which means that the inverse of that inverse is also going to be open, since these original neighborhoods are going to be open. So knowing that, we can say that if we apply f to u1, which is this neighborhood, and we apply f to u2, which is this neighborhood around y2, the neighborhoods that they map to are also going to be open and disjoint based on this previous line here. So since we've shown that for every single u1 and u2 around some arbitrary points, that means that it's the case for all of them. And since these neighborhoods are open and disjoint, that means by definition they must be Hausdorff. So we have our 2 neighborhoods around here, which when we apply f to f inverse, we get, which we are saying is the same thing as the inverse of applying the inverse. So It's a little bit confusing. It might take some staring at it for a moment. Since we've shown that they're open and disjoint, now we know that if we have open and disjoint neighborhoods and we have a homeomorphism between them, in which we have continuous functions that go both one way and the other, and remember this is continuous in the context of topology, so not exactly the same as calculus or analysis or something like that. We can say that both of these spaces are Hausdorff. So this next one is going to be a little bit more complicated. We're going to talk about Brouwer's n-dimensional fixed point theorem. That's a mouthful, but this might be oversimplifying it, but it essentially says that you can apply the intermediate value theorem in such a way to n dimensions so that at some point you get f of x must equal x, which is to say that with a continuous function, no matter what dimension you're working in, 1, 2, 3, a million, there's going to be some function that exists which sends a point to itself. Physically speaking, that means that one of the most popular ones is that if you have a map flattened out on a table and then you crumple it up any which way you like, that means there's going to be some point on that crumpled up map which is resting exactly over its original spot when it was laid flat on the table. You can say the same thing for a sphere, and then you crumple it up. There will be some spot in your crumpled up sphere that's directly underneath the spot where it was, like its projection onto the table where you crumpled it will be in the same exact spot. So it's a little mind-bending, but we're going to prove it for one dimension because proving it for higher dimensions is a little bit more intensive. Don't have time for that, and this is wonky as it is. So let's hop into it. So let's establish a few things. So first we want to establish a function from some Bn to itself. Doesn't matter what n is, that's why it's called n-dimensional. Doesn't matter what dimension we're working in. And this space is going to be comprised of basis elements of balls in Rn, of course. So what we're saying is, if this is the case, then there will exist an x such that f of x is equal to x. I should say some x in our set of bases. All right. So we've already established that f is continuous. Let's come up with another function. In this case, we're going to use a closed interval, so it includes its endpoints from -1 to 1. So we'll call that g. So we have g from -1 to 1. And we're going to define g as g of x is equal to f of x minus x. Sorry. And I'm going to go through this step by step because if I were to just make this next jump, it's going to be really confusing and not obvious at all as to how I got here. This is going to be continuous. So let's first look at just f of x, all right? We're not going to think about g of x just yet. So let's think about f of x. So if we put in -1 as our input, our output must be at least -1. Because if we put in -1 as our input, well, that's the end of our interval. We can't be anything beneath it, and it's continuous, which means that its output is also going to be mapped to the same interval. So it must be greater than or equal to 1. We make a similar argument for f of 1. So this is the upper bound, you could call it, of our interval. And since f is continuous, then that means its output must absolutely be less than or equal to 1 because there's nowhere higher for it to go. This is what we're limited to, and it's continuous. So, since that is the case, So since we made these claims and we substantiated them regarding f, that means that if we plug in -1 for g up here, we have g of -1 is going to be equal to f of -1 minus -1. We can just turn this into a positive. Use our algebra. So that means that f of -1 plus 1 is going to be at least 0. And that's because if we look back at f of -1, f of -1 must be at least -1. And if we add 1 to -1, that means it's going to be at least 0. And we can make a similar argument for g of 1. So we can say that g of -1 is going to be equal to f of -1 minus 1, and that must be less than or equal to 0, because f of 1 we said is at most 1, and 1 minus 1 therefore must be at most 0. So that means we come to our fabulous conclusion. I'm gonna boil these lines down because there's a lot of inequalities going on here. So I'm going to boil these two lines down to say that g of -1 must be at least 0, and g of 1 can only be at most 0. So now we're going to apply the IVT, the intermediate value theorem, which says that if our function spits out a negative value at some point and a positive value at another point, then at some point in between those two inputs, there must be something that gives an output of 0, which we know from calculus, which means that we're going to call some point which gives an output of 0 c, because we don't know what it is, we just know that it exists. So we know that g of c will equal 0 if and only if f of c minus c equals 0. So we're saying that this number exists and it gives an output of 0, but using the definition of g of x, we know that if this equals 0, then this must also equal 0, because they equal the same thing. So this can only be the case if and only if f of c equals c. And let's draw our nice QED, because we did so well. And that's the end of the proof. So we've shown in one dimension, but this applies to any dimension, that if we have a continuous function and we have some basis elements with an element in that basis, that if our function gives us a negative value at some point and a positive value at another, that means it must give us 0 at some point. And there must be some function that exists for which the input is the same as the output. And that's all there is to it. So thanks for watching. Hope you enjoyed. I'll make a Graph Theory 1 at some point. I skipped class to do this. And yeah, thanks for watching. See you later.